Somewhere in our galaxy right now, there is an object no wider than a small city, spinning hundreds of times every single second. And each time it turns, it fires a beam of radiation so intense it can be detected from thousands of light years away. It has been doing this for longer than human civilization has existed. It does not slow to rest, it does not flicker out, it sweeps through the darkness with the regularity of the most precise clock ever built. And in some cases, it keeps better time than anything human engineers have ever constructed. It is called a pulsar. And what makes a pulse is not what most people think, because a pulsar is not some exotic, unexplained phenomenon. It is a dead star. And the reason it never truly stops is terrifying. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something that might surprise you. A pulsar is not a special kind of object. It's not some mysterious cosmic engine that physicists build a separate category for. A pulsar is a neutron star. That's it. It's a neutron star that happens to be aimed at us. Every pulsar ever discovered is a neutron star. Not every neutron star is a pulsar, but every pulsar is a neutron star. The difference between a pulsar and a neutron star that doesn't pulse has nothing to do with what the object is made of. It has nothing to do with its internal composition or its mass or its age. The difference is geometry. It's about where we happen to be standing relative to the beams of energy that the neutron star sends out into space. If one of those beams sweeps across Earth as the star rotates, we see a pulse. If the beams miss us entirely, we never know the pulsar is there. It's the same object either way. The only difference is our line of sight. This is important to understand right from the start because pulsars are often talked about as though they're something separate from neutron stars, as though they belong in their own exotic category alongside black holes, quasars, and other things that sound like science fiction. But they don't. A pulsar is a neutron star doing what neutron stars do. It spins. It has an incredibly powerful magnetic field. And that magnetic field channels radiation into beams that sweep through space like the beam of a lighthouse on a dark coast. If you're standing on the shore and the beam crosses your eyes, you see a flash. If you're standing behind the lighthouse, you see nothing. The lighthouse is the same either way. Only your position has changed. So to understand a pulsar, you first need to understand what a neutron star is. And to understand a neutron star, you need to understand what happens when a massive star dies. Because a neutron star is not born from nothing. It's the remnant, the leftover core, of a star that once burned with extraordinary brilliance and then destroyed itself in one of the most violent events the universe can produce. Stars spend most of their lives in a delicate balance. They have enormous mass, which means gravity is constantly trying to crush them inward, trying to pull every atom toward the center. If gravity were the only force acting on a star, it would collapse into a tiny point almost instantly. But gravity is not the only force. In the core of a living star, nuclear fusion is happening. Hydrogen atoms are being forced together under tremendous pressure and temperature, fusing into helium, releasing energy in the process. That energy radiates outward as light and heat, and it creates pressure, an outward push that resists gravity. As long as fusion is producing energy, this outward pressure balances the inward pull of gravity. The star remains stable. It shines steadily for millions or billions of years, depending on how massive it is. Our sun has been doing this for about 4.5 billion years, and will continue for roughly another 5 billion. But fusion cannot last forever. A star has a finite amount of fuel. When a star like our sun exhausts its hydrogen fuel, it swells into a red giant, sheds its outer layers, and leaves behind a white dwarf, a dense but relatively quiet remnant about the size of Earth. It's a peaceful death as cosmic deaths go. The star fades, it cools, it slowly dims over trillions of years. No explosion, no catastrophe. But stars much more massive than the sun, stars with roughly 8 or more times the sun's mass, die very differently. These massive stars burn through their fuel much faster than smaller stars. A star with 20 times the mass of the sun might exhaust its hydrogen in only a few million years, compared to the sun's 10 billion. And when a massive star runs out of hydrogen in its core, it doesn't simply stop fusing. It starts fusing heavier elements. Helium fuses into carbon. Carbon fuses into neon. Neon fuses into oxygen. Oxygen fuses into silicon. Each new fuel burns faster than the last. The star races through its fuel reserves at an accelerating rate. The final stage, silicon fusing into iron, lasts only about a single day. One day. After millions of years of steady burning, the final act of fusion in a massive star is over in roughly 24 hours. And then everything stops. Because iron is different from every other element the star has been fusing. Every previous fusion reaction released energy. That energy supported the star against gravity. But fusing iron does not release energy. It absorbs energy. When the core fills with iron, fusion can no longer produce the outward pressure that has been holding the star up against its own gravity for millions of years. The balance is broken. Gravity wins. What happens next occurs in less than a second. The iron core, which at this point is roughly the size of Earth and contains about 1.5 times the mass of the sun, collapses. It doesn't collapse slowly. It doesn't take hours or days. It collapses at a significant fraction of the speed of light. The outer parts of the core fall inward at speeds reaching 70,000 kilometers per second. That is nearly a quarter of the speed of light. In roughly 1/10 of a second, the core goes from being the size of Earth to being a ball roughly 12 miles across. 12 miles. A distance you could cover on a bicycle in under an hour. The entire core, 1.5 solar masses of matter, compressed into a sphere about the size of a city. Try to picture this. You could drive across it in 15 minutes at highway speed. Manhattan Island is about 13 miles long. The core of a dead star, containing more mass than the sun, is compressed to a size smaller than Manhattan. The compression is so extreme that individual atoms cannot survive. Under the incredible pressure, the electrons are forced into the protons, combining to form neutrons through a process called inverse beta decay. The entire core becomes a ball of neutrons packed together so tightly that they're essentially touching. This is a neutron star. But we shouldn't forget what happens to the rest of the star during this collapse. The core falls inward, but the outer layers of the star are still there, still falling toward the center. When the collapsing core reaches neutron density, it suddenly becomes incredibly rigid. It can't be compressed any further. The infalling outer layers slam into this rigid neutron core and bounce off it like a ball hitting a wall. This rebound, combined with an enormous flood of neutrinos released during the neutron formation, drives a shockwave outward through the rest of the star. That shockwave tears the star apart, The outer layers are blasted into space at speeds of tens of thousands of kilometers per second, creating an expanding cloud of debris called a supernova remnant. The explosion is so bright that for a few weeks, a single supernova can outshine an entire galaxy of hundreds of billions of stars. It is one of the most energetically violent events in the known universe, and at the center of all that destruction, sitting calmly in the expanding debris cloud, is the neutron star. Tiny, unbelievably dense, spinning rapidly, and very much still there. The density is beyond anything you can find on Earth or anywhere else in the universe, short of a black hole. A single teaspoon of neutron star material will weigh roughly 4 billion tons. Not million, billion. If you could somehow scoop out a teaspoon of this material and place it on the surface of Earth, it would weigh more than every building in every city on the planet combined. That single teaspoon would weigh more than the entire population of Earth, multiplied many times over. The density of neutron star material is roughly 400 trillion times the density of water. To put that in another way, if you took every human being on Earth, all 8 billion of us, and compressed that combined mass to the density of neutron star matter, it would fit inside a single sugar cube. The gravitational pull at the surface of a neutron star is about 200 billion times the gravitational pull at the surface of Earth. If you dropped an object from a height of 1 meter above the surface of a neutron star, it would hit the surface traveling at roughly 7 million kilometers per hour. The impact energy from dropping a small marshmallow onto a neutron star from that height would release energy equivalent to several tons of high explosives. The escape velocity, the speed you'd need to travel to leave the surface, is about 1/3 the speed of light. That's roughly 100,000 kilometers per second. For comparison, the escape velocity from Earth's surface is only about 11 kilometers per second. A neutron star's gravity is in a completely different universe of intensity from anything in our everyday experience. If you were falling toward a neutron star long before you reach the surface, the difference in gravitational pull between your head and your feet would be so extreme that it would stretch your body into a thin strand of atoms. Physicists call this spaghettification. You would be torn apart by tidal forces far beyond any material's ability to resist. The surface of a neutron star is also extreme in ways that are difficult to imagine. The outer layer, called the crust, is made of iron nuclei arranged in a crystalline lattice, essentially a solid shell of iron compressed to densities millions of times greater than any material on Earth. This crust is incredibly hard. The material is so compressed and the gravity so intense that the tallest possible mountain on a neutron star would be only a few millimeters high. The surface is almost perfectly smooth, not because it was polished, but because gravity simply will not allow any significant irregularity to exist. Any bump, any hill, any deviation from a perfect sphere would be crushed flat almost instantly by the overwhelming gravitational force. Beneath the crust, the material becomes even stranger. As you go deeper, the density increases. The neutrons are packed more and more tightly together. In the outermost part of the interior, you have a neutron fluid, a sea of neutrons that behaves like a superfluid, a quantum state of matter with zero viscosity that flows without any friction whatsoever. This neutron superfluid has properties unlike any material on Earth. It can flow through the tiniest cracks and channels without losing any energy. It can rotate in quantized vortices, tiny spinning whirlpools of neutron fluid that carry angular momentum. At the very center of the neutron star, in the innermost core, the densities become so extreme that we genuinely don't know what exists there. The pressure is so high that even neutrons might break apart into their constituent quarks. There might be a core of free quarks swimming in a quark gluon plasma, a state of matter that hasn't existed freely in the universe since the first microseconds after the Big Bang. Or the neutrons might remain intact but take on exotic configurations that we don't have the physics to fully describe yet. The interior of a neutron star is one of the most extreme environments in the known universe, and despite decades of research, we still don't fully understand what happens at the very center. Now, here is where things get critical for understanding pulsars. When that massive star's core collapses, something extraordinary happens to its rotation. The original star was spinning. All stars spin. Our sun rotates roughly every 25 days at its equator. Massive stars rotate too, some of them quite rapidly. But when the core collapses, the star's rotation doesn't just continue at the same rate. It speeds up dramatically, enormously, by a factor that seems almost unbelievable. This is because of a fundamental principle of physics called conservation of angular momentum. Angular momentum is a measure of how much rotational motion an object has. It depends on two things: the mass of the object and how that mass is distributed relative to the axis of rotation. When a spinning object contracts and its mass moves closer to the axis of rotation, it must spin faster to conserve angular momentum. This is the same principle you see when a figure skater pulls her arms in during a spin. When her arms are extended, she spins slowly. When she pulls them tight against her body, bringing her mass closer to the rotation axis, she spins much faster. The total angular momentum stays the same, but because the mass is distributed differently, the rotation speed changes. Now think about the scale of what's happening when a star's core collapses. The original core might be roughly the size of Earth, maybe 10,000 kilometers across. It collapses to about 20 kilometers across. That's a reduction in radius by a factor of roughly 500. Because angular momentum is conserved, and angular momentum depends on the square of the radius, the rotation speed increases by the square of that factor. 500 squared is 250,000. So if the original core was rotating once every few hours, the neutron star might rotate several times per second. Or faster. Much faster. Some neutron stars are born spinning dozens of times per second. And some, through processes we'll explore later, spin hundreds of times per second. Hundreds of complete rotations every single second. Think about what that means physically. An object 12 miles across with a mass greater than the sun, completing a full rotation in just a few milliseconds. The surface at the equator of such a rapidly spinning neutron star would be moving at a significant fraction of the speed of light. The forces involved are staggering. Only the incredibly intense gravity of the neutron star prevents it from tearing itself apart from the centrifugal force of its own rotation. This rapid rotation is one half of what makes a pulsar. The other half is the magnetic field. And the magnetic field of a neutron star is something that deserves its own careful explanation, because it's not just strong. It is strong in a way that reshapes the very space around the star. The original massive star had a magnetic field. All stars do. The sun, for example, has a magnetic field that's responsible for sunspots, solar flares, and the beautiful arcing prominences you can see in images from solar observatories. The Sun's magnetic field at its surface is roughly a few Gauss. By comparison, a typical refrigerator magnet is about 50 Gauss, and the strongest continuous magnetic fields produced in laboratories on Earth are about 450,000 Gauss. When the star's core collapses, the magnetic field doesn't disappear. It gets compressed along with everything else. And just like angular momentum is conserved during the collapse, magnetic flux is approximately conserved as well. The magnetic field lines that were spread across a core the size of Earth are now compressed into a sphere 20 kilometers across. The field strength increases by roughly the square of the ratio of the radii, just like the rotation speed. The result is a magnetic field that is almost incomprehensibly strong. A typical neutron star has a magnetic field of about 1 trillion Gauss. That's 1 followed by 12 zeros. Some neutron stars, called magnetars, have fields reaching 1 quadrillion Gauss or more. But even a standard neutron star's magnetic field is trillions of times stronger than any magnetic field that exists naturally on Earth. To give you a sense of what this means, at the surface of a neutron star, the magnetic field is strong enough to fundamentally alter the structure of matter. Atoms cannot maintain their normal spherical shape. The field distorts the electron clouds, stretching atoms into elongated cylinders aligned with the field direction. Chemical bonds, as we know them, cease to function normally. Your body's chemistry would simply stop working. Water molecules would be deformed beyond recognition. Even at a few hundred kilometers from the surface, the field remains strong enough to affect atomic structure in measurable ways. And the radiation environment near a magnetized neutron star, the intense X-rays and gamma rays produced by particles spiraling along field lines, would be lethal at distances far greater than 1,000 kilometers. The physics of matter in these conditions is bizarre and alien, governed by rules that have no counterpart in our everyday experience. This magnetic field does something crucial. It reaches far out into the space surrounding the neutron star, creating a structure called the magnetosphere. The magnetosphere extends for thousands of kilometers around the star, and it is filled with charged particles that are trapped and accelerated by the magnetic field. These particles, electrons and positrons, are ripped from the neutron star's surface or created in the intense electromagnetic fields near the star. And they spiral along the magnetic field lines at velocities approaching the speed of light. And here is where the pulsar phenomenon begins to take shape. Because the magnetic field has poles, just like a bar magnet has a north pole and a south pole. The magnetic field is strongest at these poles. Charged particles are funneled along the field lines toward the magnetic poles, accelerated to extreme energies. When these particles reach the polar regions, they emit intense radiation. The radiation is focused into narrow beams emanating from the magnetic poles, like twin searchlights extending out from the neutron star in opposite directions. Now, here is the detail that makes pulsars possible. In almost every neutron star, the magnetic axis is not aligned with the rotation axis. The magnetic poles are tilted relative to the spin poles. They're offset by some angle, sometimes a small angle, sometimes nearly 90 degrees. This misalignment is not unusual or surprising. Earth's magnetic poles are offset from its geographic poles by about 11 degrees. The Sun's magnetic axis is tilted relative to its rotation axis too. It would be far stranger if the axes were perfectly aligned. Perfect alignment would require extraordinary symmetry in the conditions during the star's collapse, and nature almost never produces that kind of perfection. This tilt is absolutely essential. Because the magnetic axis is tilted relative to the rotation axis, the beams of radiation do not point in a fixed direction. They sweep through space as the neutron star rotates, tracing out a cone in three-dimensional space. Each time the neutron star completes one full rotation, the beams sweep around once. If Earth happens to lie somewhere along the path that the beam traces as it sweeps around, we see a flash of radiation each time the beam crosses our line of sight. One flash per rotation. That flash is the pulse. That is what a pulsar is. A rotating neutron star with a tilted magnetic field whose radiation beams sweep across our position with each spin. The regularity of the pulses comes directly from the regularity of the rotation. As long as the star spins at a constant rate, the pulses arrive at a constant rate. And neutron stars, being incredibly dense and compact, spin with extraordinary stability. There's very little to slow them down in the vacuum of space. No air resistance, no friction, just the cold emptiness of the void and the star spinning in it, sending its beams sweeping outward with mechanical precision. The moment a pulsar was first detected, it confused everyone. In 1967, a graduate student named Jocelyn Bell Burnell was working with a radio telescope at the Mullard Radio Astronomy Observatory in Cambridge, England. The telescope was designed to study quasars, distant galaxies with extraordinarily bright cores. Bell Burnell noticed something strange in the data. There was a signal, a repeating radio pulse, arriving with an almost perfect period of about 1 1/3 seconds. The signal was so regular, so precise, that Bell Burnell and her supervisor Anthony Hewish initially couldn't believe it was natural. No known natural phenomenon produced such clock-like regularity. For a brief time, they half-jokingly labeled the signal LGM1, which stood for Little Green Men 1, because the regularity seemed almost artificial, almost like a beacon from an intelligent civilization. But it wasn't aliens. More pulsating sources were quickly found in different parts of the sky, all with different periods, but all with the same clock-like regularity. Whatever these objects were, they were natural, and they were common. The explanation came from astrophysicists Thomas Gold and Franco Pacini, who independently proposed that the pulsars were coming from rapidly rotating neutron stars. Gold argued that the rotation of a highly magnetized neutron star with misaligned magnetic and rotation axes would naturally produce a sweeping beam of radiation that an observer would perceive as a pulse. The period of the pulse would correspond exactly to the rotation period of the star. This model explained everything. The regularity, the short period, the fact that the periods were slowly increasing over time, which made sense if the stars were gradually losing rotational energy. The rotating neutron star model was accepted quickly because it explained the observations so perfectly. That first pulsar, now designated PSRB 1919+21, is still being observed today, decades later. It's still pulsing. It's still sweeping its beams through space with the same clockwork precision. The period has increased slightly over the decades because the star is gradually losing rotational energy. But the change is tiny. The pulsar is still very much active, and it will remain active for a very long time yet. Since that first discovery, astronomers have found more than 3,400 pulsars in the Milky Way and its neighboring galaxies. They come in a wide range of rotation periods. From the slow rotators that spin once every few seconds, to the extraordinary millisecond pulsars that complete hundreds of rotations every second. They're found in many different environments. Some are isolated, drifting alone through the galaxy. Some are in binary systems, orbiting a companion star. Some are at the centers of supernova remnants, surrounded by the expanding debris of the explosion that created them. Some are in globular clusters, dense collections of old stars where gravitational interactions are common. But every single one of them is the same thing at its core. A neutron star. A dead stellar core. An object roughly 12 miles across, more massive than the Sun, spinning rapidly, with a magnetic field trillions of times stronger than Earth's, sending beams of radiation sweeping through the cosmos with each rotation. The word pulsar is actually a shortened form of pulsating star, but the name is slightly misleading. A pulsar doesn't actually pulsate. It doesn't expand and contract or flash on and off. The emission is continuous. The beams are always on, always shining, always radiating energy from the magnetic poles. What pulses is our detection of that emission. The beam sweeps across us and then sweeps away, creating the appearance of a flash from our perspective. But from the neutron star's perspective, nothing is flashing. The beams are steady. It's only because of the rotation and the tilt of the magnetic axis that we perceive them as pulses. This is a crucial distinction. The pulsar isn't blinking at us like a signal light. It's rotating, and its beams are sweeping across our line of sight with each turn. The pulse is a consequence of geometry and rotation, not of the star turning its emission on and off. Understanding this distinction is essential to understanding everything else about pulsars, from their incredible regularity to their gradual slowdown, to the reasons why some pulsars can persist for billions of years. And that regularity is something that genuinely shocked astronomers when pulsars were first studied carefully. Because the precision of pulsar timing turned out to be extraordinary. Not just good, not just impressive, but in some cases, competitive with the best atomic clocks on Earth. That level of precision, coming from a dead star spinning in the vacuum of space, opened up entirely new ways of studying the universe. It turned pulsars from curiosities into precision instruments, tools for testing general relativity, detecting gravitational waves, and probing the structure of space-time itself. But to understand how pulsars became such powerful tools, you first need to understand the mechanism in more detail. You need to understand exactly how those beams are generated, what determines their shape and intensity, and why the geometry of the magnetic field relative to the rotation axis is so important. Because the story of a pulsar is ultimately a story about misalignment. About two axes that refuse to line up. And that simple geometric fact, that refusal to be perfectly symmetrical, is what makes the entire phenomenon possible. Without that tilt, there would be no sweeping beam, no pulse, no signal reaching across the galaxy to announce the presence of a dead star still spinning in the dark. So now we know what a pulsar is. A neutron star. A dead stellar core about 12 miles across, more massive than the Sun, spinning rapidly, and surrounded by a magnetic field of almost unimaginable intensity. But knowing what a pulsar is made of doesn't fully explain why it pulses. Saying a pulsar flashes because it spins is like saying a car moves because it has an engine. It's technically true, but it skips over the most important part, the mechanism. The actual physical process by which a spinning, magnetized neutron star produces focused beams of radiation that sweep through space like searchlights in the dark. That mechanism is what we need to understand now, because once you understand how these beams are created, everything else about pulsars falls into place. Let's start with the magnetic field. We've already established that neutron stars have magnetic fields trillions of times stronger than Earth's. But what does that actually mean in physical terms? What does a magnetic field that strong do to the space around a neutron star? On Earth, magnetic fields are familiar. You've played with bar magnets. You've seen iron filings line up along magnetic field lines. Earth itself has a magnetic field generated by the motion of liquid iron in its core. That field extends far out into space, creating a magnetosphere that deflects the solar wind and protects our atmosphere. Earth's magnetic field at the surface is about half a Gauss, incredibly weak by cosmic standards. A neutron star's magnetic field is roughly 1 trillion Gauss. That's about 2 trillion times stronger than Earth's surface field. They're technically the same kind of thing, but the scale is so vastly different that they behave in fundamentally different ways. At these field strengths, the magnetic field doesn't just passively fill the space around the neutron star. It dominates that space. It controls the motion of every charged particle in the vicinity. It shapes the flow of energy. It essentially creates a structured environment around the star, a magnetosphere that extends thousands of kilometers into space, and within which the magnetic field dictates everything that happens. Nothing moves in the magnetosphere of a neutron star without the magnetic field's permission. Every electron, every positron, every charged particle is forced to follow the magnetic field lines, spiraling around them in tight helical paths. The particles cannot move across the field lines. They can only move along them. The magnetic field acts as a set of invisible tracks, rigid channels along which particles are forced to travel. This is very different from how particles behave near Earth. Near a neutron star, the field is so overwhelmingly strong that particles are essentially locked to their field lines. They spiral around a single field line with a gyration radius so small it's measured in fractions of a millimeter. The particles are trapped so tightly that they might as well be threaded on invisible wires extending from the neutron star's surface out into space. Now let's think about what this means near the magnetic poles. A magnetic field has a specific geometry. The field lines emerge from one magnetic pole, arc outward through space, and curve back down to enter the other magnetic pole. Near the equator of the star, the field lines extend far out into space before curving back. But near the magnetic poles, the field lines are concentrated. They converge, bunching together, creating regions of especially intense magnetic field. If you could see the field lines, they would look like the bristles of a brush near the poles, dense, tightly packed, and pointing nearly straight outward from the surface. Charged particles in the magnetosphere are channeled by these field lines. Particles that are far from the poles spiral along field lines that arc far out into space. But particles near the magnetic poles are funneled downward along converging field lines toward the polar surface, or accelerated outward along field lines that extend nearly straight away from the star. The magnetic poles act as funnels, concentrating particle flow into narrow columns above and below the magnetic pole regions. But where do these charged particles come from in the first place? The neutron star is sitting in the vacuum of space. There's very little matter around it. So how does it generate the particles that fill its magnetosphere and ultimately produce its radiation beams? The answer is that the neutron star creates its own particles, and it does this through a process so extreme that it sounds more like science fiction than physics. The rapidly rotating magnetic field of a neutron star generates enormous electric fields. This is a direct consequence of fundamental electromagnetism. When a magnetic field changes with time, or when a conducting body moves through a magnetic field, electric fields are induced. A neutron star is a highly conducting body rotating in its own intense magnetic field. The rotation induces electric fields at the star's surface that are extraordinarily powerful. These induced electric fields can reach 1 trillion volts per meter or more near the magnetic poles. The strongest electric fields we could sustain in laboratories on Earth are about 100 million volts per meter. A neutron star generates fields 10,000 times stronger than that, continuously, across its surface. These immense electric fields are strong enough to rip charged particles directly from the neutron star's surface. Electrons are pulled from the iron lattice of the crust and accelerated to tremendous speeds along the magnetic field lines near the poles. The force exerted by these electric fields on surface particles vastly exceeds the neutron star's already formidable gravitational pull. Even though the surface gravity is 200 billion times Earth's gravity, the electric field near the poles can overcome it. Particles are literally torn from the surface against gravity that would crush a human being into a film of atoms. Once these electrons are pulled from the surface and accelerated along the magnetic field lines, something remarkable happens. As the electrons move along the curved magnetic field lines, they emit radiation. Any charged particle that is accelerated emits electromagnetic radiation. This is a fundamental law of physics called Larmor radiation. The electrons spiraling along the field lines near the magnetic poles are being continuously accelerated by the curvature of the field lines and by the magnetic field itself, so they continuously emit photons. But the radiation process near a neutron star is far more extreme than ordinary Larmor radiation. The particles are accelerated to such high energies, reaching velocities extremely close to the speed of light, that they emit high-energy gamma-ray photons. These gamma-ray photons are so energetic that they do something extraordinary. When a high-energy gamma-ray passes through the intense magnetic field near the neutron star, it can spontaneously convert into a pair of particles, an electron and a positron. This process is called magnetic pair production. It happens because the energy of the gamma-ray photon is sufficient in the presence of the strong magnetic field to create matter directly from light. Energy becomes matter. Energy becomes mass, exactly as Einstein's famous equation E equals mc squared predicts. These newly created electrons and positrons are themselves accelerated by the electric field and emit their own gamma-ray photons. Those gamma rays can produce more electron-positron pairs. Those new pairs are accelerated and emit more gamma rays. A cascade develops, a chain reaction of particle creation and radiation. This cascading process is called a pair cascade, and it floods the region above the magnetic poles with a dense plasma of electrons and positrons, all moving at nearly the speed of light, all radiating intensely. This is the engine of a pulsar. The pair cascade above the magnetic poles creates a column of ultra-relativistic particles. Particles moving at velocities so close to the speed of light that their mass has increased many times over due to relativistic effects. These particles are confined to a narrow column by the converging magnetic field lines near the pole. They can't spread out sideways because the magnetic field won't let them. They can only stream outward along the pole in a tight beam. As these ultra-fast particles stream outward along the open magnetic field lines above the magnetic poles, they produce radiation through several mechanisms. One is curvature radiation. The particles follow the curved magnetic field lines, and the curvature of their path causes them to emit radiation. Because the particles are traveling at nearly the speed of light, this radiation is highly beamed in the forward direction of their motion. It doesn't radiate equally in all directions. It's concentrated into a narrow cone aimed along the direction the particles are traveling. This is a relativistic effect. When a particle moves at close to the speed of light, the radiation it emits is compressed into a narrow beam pointing in the direction of motion. It's similar to how the sound from a supersonic jet is compressed into a cone. The faster the particle moves, the narrower the beam. Another mechanism is synchrotron radiation. The particles spiral around the magnetic field lines, and this spiraling motion produces radiation. In the incredibly strong magnetic field near a neutron star, synchrotron radiation can be extremely intense, producing photons across a wide range of energies from radio waves to X-rays and gamma rays. There's also a process called inverse Compton scattering, where the ultrafast particles collide with lower energy photons near the neutron star's surface and boost those photons to much higher energies. These upscattered photons add to the beam's intensity. The combined effect of all these radiation processes is a tight, intense beam of electromagnetic radiation emanating from each magnetic pole. The beam is not wide and diffuse, it's focused and directional. Imagine a flashlight beam, except instead of visible light, it contains radio waves, X-rays, and gamma rays. And instead of being produced by a battery and a bulb, it's produced by a trillion Gauss magnetic field, ripping particles from the surface of a dead star and accelerating them to nearly the speed of light. The opening angle of the beam, how wide it spreads, depends on several factors, including the neutron star's rotation period and the geometry of its magnetic field. Typical beam opening angles range from about 5 degrees to perhaps 30 degrees. Some are wider, some are narrower. But in all cases, the beam covers only a fraction of the full sky as seen from the neutron star. The radiation is not emitted in all directions, it's channeled into two opposing beams, one from each magnetic pole, each pointing outward along the magnetic axis. And this is where the misalignment becomes everything. We've established that the magnetic axis and the rotation axis point in different directions, but now we need to understand this geometry precisely, because the exact angle between these axes determines what any given observer sees. The rotation axis is fixed by the angular momentum of the original collapse. The magnetic axis is fixed by the field geometry frozen into the core, and there's no physical reason for these two directions to coincide. The angle between the magnetic axis and the rotation axis is called the obliquity angle, or the inclination angle. It can be anything from 0 degrees, meaning perfectly aligned, to 90 degrees, meaning the magnetic axis is perpendicular to the rotation axis. In reality, most neutron stars have obliquity angles somewhere between these extremes, typically ranging from about 10 to 60 degrees based on observations, though it's often hard to measure precisely. Because the magnetic axis is tilted relative to the rotation axis, the magnetic poles trace out circles in space as the star rotates. Imagine holding a flashlight and tilting it at an angle, then spinning around in place. The beam of the flashlight would trace out a cone shape in the air around you. That's exactly what happens with a pulsar's radiation beams. Each beam sweeps out a cone as the star rotates. The opening angle of this cone depends on the obliquity angle between the magnetic and rotation axes. Now consider an observer. Say an astronomer on Earth with a radio telescope. That observer is sitting at some fixed point in space. The pulsar is spinning, and its beams are sweeping through space, tracing out cones. If the observer happens to be located somewhere within the cone traced by one of the beams, then once per rotation, the beam sweeps across the observer's line of sight. The observer detects a brief flash of radiation, a pulse. The pulse lasts only for the fraction of the rotation during which the beam is aimed at the observer. Then, the beam sweeps past, and the observer detects nothing until the next rotation brings the beam around again. One pulse per rotation. If the pulsar rotates once per second, the observer detects one pulse per second. If it rotates 30 times per second, the observer detects 30 pulses per second. The pulse period is exactly equal to the rotation period of the neutron star. If the observer is not located within the cone traced by either beam, then the beams never sweep across the observer's line of sight. The observer never detects a pulse. The neutron star is still there, still spinning, still radiating, but the observer has no way of knowing it's a pulsar. From that observer's perspective, the neutron star is invisible at radio wavelengths. It's a silent spinner in the dark. This geometric selection effect is extremely important. It means that we only see a fraction of all the neutron stars in the galaxy as pulsars. The fraction we can detect depends on how wide the beams are and what the distribution of obliquity angles is. Estimates vary, but astronomers generally think that for any given pulsar, the beam sweeps across only about 20 to 30% of the full sky. This means roughly 70 to 80% of all pulsars in the galaxy are invisible to us. Their beams never point our way. We know they're out there statistically, but we can never detect their pulsars from Earth. There are probably hundreds of thousands of active pulsars in the Milky Way that we will never see because of geometry alone. They're spinning, they're beaming, they're doing everything a pulsar does, but their beams miss us entirely. This also means that the 3,400 or so pulsars we've discovered represent only a small fraction of the total population. The actual number of active neutron stars in the Milky Way that would appear as pulsars, if viewed from the right angle, is estimated to be around 100,000 to 200,000. We're seeing only the tip of the iceberg. There's a wonderful irony in this. The most famous property of pulsars, the thing that gives them their name, has nothing to do with the neutron star itself changing. It's entirely about our position. And this has a profound consequence that most people don't consider. It means we're missing most of the pulsars in the galaxy. If your line of sight doesn't intersect the cone traced by the beam, the pulsar is invisible to you. You'd never know it existed. If you could somehow view a pulsar from directly above one of its magnetic poles, looking straight down the beam, you wouldn't see pulsars at all. You'd see a steady source of radiation that never varied. It would look like a constant point of light, not pulsing at all. This geometric dependence shapes everything about how we study pulsars. It means that what we observe is filtered by our viewing angle. Pulsars seen nearly pole-on produce wide, gentle pulses. Pulsars seen at a grazing angle produce sharp, narrow pulses. The same object looks different depending on where you're standing. The pulse is a shadow play of geometry and rotation, carrying information about angles and distances encoded in its shape and timing. Now let's think about what the radiation actually consists of. Pulsars emit radiation across a remarkably broad range of the electromagnetic spectrum. The first pulsars were detected at radio wavelengths, using radio telescopes sensitive to frequencies of a few hundred megahertz. Radio emission remains the most common way pulsars are detected, and most known pulsars are radio pulsars. But many pulsars also emit at much higher energies. Some emit in the infrared. Some emit visible light. Some emit ultraviolet radiation. Some emit X-rays. And some emit gamma rays, the highest energy form of electromagnetic radiation. The Crab Pulsar, located at the center of the Crab Nebula, about 6,500 light-years from Earth, is one of the most extensively studied pulsars in the sky. It was created by a supernova explosion that was observed and recorded by Chinese astronomers in the year 1054. Japanese and possibly Middle Eastern observers noted it as well. The explosion produced a new star so bright it was visible during the day for about 23 days. Nearly 1,000 years later, the remnant of that explosion is still visible as the Crab Nebula, a beautiful, expanding cloud of gas and dust. And at the center of that cloud sits the Crab Pulsar, spinning about 30 times per second. The Crab Pulsar emits radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. It's one of the few pulsars that can be detected in visible light, appearing as a faint star that flickers 30 times per second. If you had a telescope and a detector fast enough, you could watch it blink. Each blink corresponds to one rotation of the neutron star, 30 rotations per second. The beam sweeping across your line of sight 30 times every second. The fact that pulsars emit across such a wide range of wavelengths tells us that multiple radiation mechanisms are at work. Radio emission, which comes from lower energy processes, is probably produced at higher altitudes in the magnetosphere, farther from the neutron star's surface, where the magnetic field is somewhat weaker. The exact mechanism for radio emission from pulsars is still debated. It probably involves coherent emission, where large numbers of particles emit radiation in sync, producing a signal much stronger than individual particles could generate alone. This coherent process is necessary because the radio brightness of pulsars is far too high to be explained by individual particles radiating independently. X-ray and gamma ray emission, on the other hand, comes from processes much closer to the neutron star's surface, where the magnetic field is strongest and particles are accelerated to the highest energies. These high-energy emissions are produced by the curvature radiation and synchrotron radiation we discussed earlier. They give us direct information about conditions in the most extreme regions of the magnetosphere, within a few hundred kilometers of the neutron star. The shape of the pulse itself, how the brightness changes during a single pulse, carries information about the geometry of the beam and the structure of the emission region. Most pulsars don't produce a simple, symmetric pulse. The pulse profile, a plot of brightness versus time during one rotation, often has a complex shape. There might be a main pulse and an interpulse, a secondary peak of emission arriving about half a rotation after the main pulse. The interpulse comes from the other magnetic pole. When both poles are visible from Earth, you see two pulses per rotation, one from each pole. The main pulse might have multiple subcomponents, smaller peaks within the overall pulse, suggesting that the emission region above the magnetic pole has internal structure. Different parts of the emission region might produce radiation at slightly different times as the beam sweeps past the observer. Some pulsars show remarkable stability in their pulse profiles. The average shape of the pulse, obtained by adding together thousands or millions of individual pulses, remains almost perfectly constant over decades. This tells us that the large-scale structure of the emission region is extremely stable. The magnetic field geometry and the particle acceleration processes are not changing in any significant way over human timescales. The neutron star has settled into a steady state, spinning, radiating, sweeping its beams through space with mechanical regularity. Individual pulses, however, can vary quite a lot. While the average pulse profile is stable, each individual rotation produces a pulse that might be stronger or weaker, wider or narrower, slightly earlier or later than average. Some rotations produce no detectable pulse at all. This phenomenon, called nulling, occurs in some pulsars where the emission seems to turn off for a few rotations and then turn back on. Some pulsars null for extended periods, going silent for minutes, hours, or even days before resuming their regular pulsing. The reasons for nulling are not fully understood, but it probably involves changes in the pair cascade process above the magnetic poles. If the cascade weakens or stops temporarily, the beam dims or disappears. When the cascade restarts, the pulse returns. There's also a phenomenon called mode changing, where a pulsar's average pulse profile switches between two or more distinct shapes. The pulsar might produce one type of pulse profile for hours or days, then abruptly switch to a different profile, then switch back. This suggests that the magnetosphere can exist in more than one stable configuration, and it occasionally flips between these configurations. The physics behind mode changing is still being actively researched. Despite these individual pulse variations, the overall timing of the pulses, the long-term regularity of the pulse arrival times, remains extraordinarily precise. The variations in individual pulses average out over many rotations. When you measure thousands of pulses and calculate the average period, the result is astonishingly stable. Pulsar timing, the careful measurement of pulse arrival times, has become one of the most precise measurement techniques in all of astronomy. The stability of these signals is so extraordinary that pulsars have become some of the most powerful tools in physics, used to probe phenomena that no earthbound instrument could detect on its own. The beams themselves are not infinitely thin pencil beams. They have a finite width, typically covering a cone of roughly 5 to 30 degrees in opening angle. The width of the beam determines how long the pulse lasts relative to the full rotation period. If the beam has an opening angle of 10 degrees and the star rotates once per second, then the pulse lasts for about 10 out of 360 degrees, which is about 28 milliseconds. That's how long the beam takes to sweep across the observer's position. For the remaining 972 milliseconds of the rotation, the beam is pointed elsewhere and the observer detects nothing. The width of the beam also determines what fraction of the sky the pulsar illuminates. A wider beam sweeps across more of the sky with each rotation, increasing the probability that a distant observer will happen to be in the path of the beam. This means wider beam pulsars are more likely to be detected. Conversely, narrow beam pulsars are harder to find because they illuminate less of the sky and are visible from fewer angles. This creates an observational bias. The pulsars we find tend to be those with wider beams because they're easier to detect. The true population of pulsars includes many with narrow beams that we're missing. Let me paint a picture of what all this would look like if you could somehow observe a pulsar up close. Not from Earth, thousands of light years away. But from a hypothetical vantage point, 1,000 kilometers from the Neutron star, you would see a small, featureless sphere, 12 miles across, glowing faintly with thermal X-ray radiation from its incredibly hot surface, almost perfectly smooth, any mountains being only millimeters tall, flattened by gravity. Extending outward from the star, you'd see the magnetic field structure. Near the equator, closed loops arcing outward and curving back. Near the magnetic poles, open field lines extending outward into space, defining the polar cap where particles can escape. Above each polar cap, a column of intensely bright radiation, a focused beam of plasma and photons shooting outward along the open field lines like a spotlight cutting through darkness. And the whole star would be spinning. If this were a typical pulsar spinning a few times per second, you'd see the beams whipping around like the lights on top of an emergency vehicle. If it were a millisecond pulsar spinning hundreds of times per second, the rotation would be so fast that the beams would appear as a nearly continuous blur. The surface at the equator would be moving at a significant fraction of the speed of light. The magnetosphere itself would be filled with structure, plasma flowing along field lines, currents of charged particles circling the star. The whole system would be a machine of extraordinary precision, powered by the stored rotational energy of the neutron star and shaped by its overwhelmingly powerful magnetic field. From Earth, all of this complexity is reduced to a single blip on a radio telescope. A brief flash of radio waves repeating at precise intervals. That blip carries information about everything happening at the neutron star, encoded in the pulsar's timing, its shape, its polarization, its spectrum. Decoding that information has been the work of pulsar astronomers for over 50 years. And the information contained in those simple blips has turned out to be among the most scientifically valuable data in all of astronomy. Because pulsars don't just tell us about neutron stars. Their extraordinary precision makes them natural laboratories for testing fundamental physics. They've been used to confirm predictions of Einstein's general theory of relativity with spectacular accuracy. They've been used to detect gravitational waves rippling through space-time. They've been used to discover the first planets ever found outside our solar system. But all of that precision, all of that scientific power depends on one thing: the regularity of the pulse. The fact that the neutron star spins at an almost perfectly constant rate, sending its beams sweeping through space with clock-like precision, rotation after rotation, year after year, century after century. That regularity is what makes pulsars useful. And understanding why pulsars are so regular, how regular they actually are, and what eventually disrupts that regularity is what we need to explore next. Because the precision of pulsars isn't just impressive, it's almost unsettling. It's the kind of precision that made the scientists who first discovered pulsars wonder whether they had found signals from an intelligent civilization. The regularity of a pulsar is so perfect, so mechanical, so unlike anything else in nature, that it demands explanation. And the explanation reveals something deep about how the universe preserves information in the spins of dead stars. When astronomers first began measuring pulsar timing with precision instruments, what they found was almost disturbing. The pulsars arrived with a regularity that seemed impossible for a natural object. Not approximately on time, not roughly periodic, not close enough for practical purposes, but precisely on time, to a degree that challenged the best timekeeping devices humans had ever built. A pulsar spinning 10 times per second doesn't drift by a few percent over the course of a year. It doesn't vary by a fraction of a percent. The arrival time of each pulse can be predicted months or years in advance, with an accuracy measured in microseconds, millionths of a second. For some pulsars, the prediction accuracy reaches nanoseconds, billionths of a second, over timescales of years. Think about what that means. An object that was created in one of the most violent events in the universe, an explosion that briefly outshone an entire galaxy, spinning in the vacuum of space with no engine, no flywheel, no stabilizing mechanism designed by engineers, keeps time with a precision that matches or exceeds the atomic clocks that define the international standard of time. An atomic clock uses the quantum vibrations of cesium atoms to keep time. It's the product of decades of engineering, operating in carefully controlled laboratory conditions, shielded from vibration and temperature changes. A pulsar is a ball of neutrons 20 kilometers across, sitting in the cold vacuum of space, and it keeps comparable time simply by spinning. The reason for this extraordinary stability is straightforward once you understand the physics. A pulsar is incredibly dense and incredibly compact. Its moment of inertia, the measure of how much its rotation resists changes, is enormous relative to any forces acting on it. Think of a spinning top, a light. Small top slows down quickly because air resistance and friction at the tip can easily overcome its rotational momentum. But imagine a spinning top, the mass of the sun, compressed into a sphere 12 miles across. The rotational energy stored in that object is staggering. Even a substantial force would take a very long time to change its spin rate appreciably. The rotational energy of a typical pulsar spinning 10 times per second is roughly equivalent to the total energy output of the sun over several million years. All of that energy is stored in the spin, and the forces acting to slow the pulsar down, while real and continuous, are tiny compared to that stored energy. It's like trying to slow down an ocean liner by blowing on it. You are applying a force, technically, but the ship's momentum is so enormous that the effect is negligible over any human timescale. Additionally, pulsars spin in a near-perfect vacuum. There's no air resistance, no friction against the surface, no bearings to wear out. The neutron star is floating in empty space, spinning freely. The only thing slowing it down is the energy it radiates away through its magnetic field. And while that energy loss is real, it happens gradually, over thousands or millions of years. On the timescale of human observations, the slowdown is tiny and incredibly predictable. Astronomers can measure the rate at which a pulsar is slowing down with extreme precision and account for it in their timing models. Once you subtract the known slowdown rate, the residual timing variations are astonishingly small. This is what makes pulsar timing one of the most powerful measurement techniques in astronomy. When you have a clock that precise, you can detect extremely subtle effects. Any tiny change in the arrival time of a pulse, even by a few nanoseconds, tells you that something has happened. Either the pulsar itself has changed in some way, or something between the pulsar and your telescope has affected the signal, or your model of the pulsar's motion through space is slightly wrong. By carefully analyzing these tiny timing variations, astronomers can extract an enormous amount of information. One of the first triumphs of pulsar timing came from a pulsar discovered in 1974 by Russell Hulse and Joseph Taylor using the Arecibo radio telescope in Puerto Rico. This pulsar, designated PSRB 1913+16, turned out to be in a binary system orbiting a companion neutron star. The two neutron stars orbit each other every 7 hours and 45 minutes, moving at speeds of up to 300 kilometers per second. This system provided a natural laboratory for testing Einstein's general theory of relativity in conditions far more extreme than anything available on Earth or in the solar system. General relativity predicts that two massive objects orbiting each other should emit gravitational waves, ripples in the fabric of space-time itself. These waves carry energy away from the system, and as the system loses energy, the two objects spiral closer together. Their orbital period decreases, they speed up. Hulse and Taylor monitored PSRB 1913+16 for years, carefully measuring the arrival times of its pulsars with extreme precision. Because the pulsar is in a binary orbit, the pulse arrival times vary as the pulsar moves toward and away from Earth during its orbit. By tracking these variations, Hulse and Taylor could measure the orbital period with extraordinary accuracy. What they found was that the orbital period was decreasing. The two neutron stars were spiraling toward each other, and the rate at which the orbit was shrinking matched the prediction of general relativity for gravitational wave emission to within a fraction of a percent. This was the first indirect detection of gravitational waves. It provided powerful evidence that Einstein's theory was correct, even in the most extreme gravitational conditions. Hulse and Taylor were awarded the Nobel Prize in Physics in 1993 for this discovery. The precision required for this measurement was extraordinary. The orbital decay amounts to a decrease of about 76 microseconds per year in the orbital period. That's 76 millionths of a second per year. Detecting such a tiny change required timing the pulsar's pulses with an accuracy better than a few microseconds over many years. Only a pulsar could provide that kind of precision. No other natural object in the universe keeps time well enough to make this measurement possible. Pulsar timing has also been used to discover planets. In 1992, astronomer Alexander Wolszczan announced the discovery of two planets orbiting a pulsar designated PSRB1257+12. These were the first confirmed exoplanets ever discovered, found before any planets were detected around normal, sun-like stars. The discovery was made entirely through pulsar timing. As the planets orbit the pulsar, their gravity tugs the pulsar slightly back and forth. These tiny motions cause the pulse arrival times to vary by small amounts. By analyzing these variations, Wolszczan could determine the number of planets, their orbital periods, and their approximate masses. The planets orbiting PSRB 1257+12 are strange worlds. They orbit a dead star, a neutron star that was born in a supernova explosion. Any planets that existed around the original star would have been destroyed in the explosion. These planets must have formed after the supernova, probably from a disk of debris left over from the explosion or from material stripped from a companion star. They orbit in a bath of intense radiation from the pulsar. They're almost certainly lifeless, barren worlds illuminated by the pulsar's beams rather than the warm light of a normal star. But the discovery proved that planets could form in the most extreme and unlikely environments, and it demonstrated the incredible sensitivity of pulsar timing. The gravitational effect of a planet on a neutron star is incredibly subtle. The pulsar barely wobbles at all. But the timing precision is so extraordinary that even this tiny wobble is detectable. Now, so far we've been talking about what you might call ordinary pulsars. These are neutron stars born in supernova explosions, spinning at rates of roughly 1 to 30 rotations per second. Their periods range from about 30 milliseconds to a few seconds. Some spin even more slowly, with periods stretching to several seconds. They have strong magnetic fields, typically around 1 trillion Gauss. They're slowing down gradually as they radiate energy through their magnetic fields. And they keep excellent time, good enough for many scientific applications. The Crab pulsar, spinning about 30 times per second, is a young, ordinary pulsar. PSRB 1919 +21, the first pulsar ever discovered, spinning about once every 1.3 seconds, is an older ordinary pulsar that has already slowed down considerably from its birth spin rate. These objects are impressive, but they're not the most extreme timekeepers in the universe. There's another class of pulsars that takes everything to an entirely different level. Millisecond pulsars. These are neutron stars that spin not a few times per second, but hundreds of times per second. The fastest known millisecond pulsar, PSRJ 1748-2446 AD, located in a globular cluster about 18,000 light-years from Earth, spins at 716 rotations per second. 716 times every single second. That means the surface at its equator is moving at a significant fraction of the speed of light, likely around 15% or more. The neutron star completes a full rotation in about 1.4 milliseconds. In the time it takes you to blink, this star has rotated about 500 times. This is an astonishing rotation rate. When you first hear it, it sounds impossible. How can anything spin that fast without flying apart? The answer goes back to the incredible density and gravity of neutron stars. The gravitational force holding the star together is so intense that even at these rotational speeds, the centrifugal force at the equator is not enough to overcome gravity. The star holds together, but just barely in some cases. There's a theoretical maximum spin rate for neutron stars, determined by the point at which the centrifugal force at the equator would equal the gravitational force. This limit is somewhere around 1,000 to 1,500 rotations per second, depending on the equation of state of neutron star matter, which is still not fully understood. The fastest known millisecond pulsars are approaching but have not yet reached this limit. Finding a pulsar that spins close to the theoretical maximum would tell us important things about the internal structure and composition of neutron stars. But here's the puzzle. If pulsars are born spinning fast and then gradually slow down over time, how can millisecond pulsars be spinning so rapidly? They should have slowed down long ago. Ordinary pulsars slow down noticeably over thousands to millions of years. A pulsar that was born spinning 30 times per second millions of years ago should now be spinning more slowly, not hundreds of times per second. Something doesn't add up. The answer is that millisecond pulsars didn't reach their current spin rates at birth. They were spun up, recycled, given a second life. And the process by which this happens is one of the most remarkable examples of stellar engineering that nature has ever produced. Here's how it works. Most millisecond pulsars are found in binary systems, orbiting a companion star. This is the first clue. Ordinary pulsars are often found alone, isolated in space. But millisecond pulsars almost always have a companion. The story goes like this. A massive star explodes as a supernova and leaves behind a neutron star. The neutron star begins its life as an ordinary pulsar, spinning rapidly and slowing down over time as it radiates energy. If the neutron star is in a binary system, it has a companion star orbiting nearby. Initially, nothing special happens. The neutron star slows down gradually, its pulsars becoming less frequent. Over millions of years, it might slow down enough that it crosses the death line, the theoretical boundary below which a pulsar can no longer generate radio emission. At that point, it goes silent. It's still a neutron star, still spinning, but no longer producing detectable radio pulsars. It becomes invisible to radio telescopes, a dead pulsar. But then the companion star evolves. All stars evolve over time, and the companion is no exception. As the companion star ages, it expands. If the companion is massive enough, or if the two stars are close enough, the expanding companion eventually reaches a critical boundary called the Roche lobe. The Roche lobe is the region around a star within which material is gravitationally bound to that star. Beyond the Roche lobe, material can flow toward the other object in the binary system. When the companion star fills its Roche lobe, matter begins streaming from the companion onto the neutron star. This transferred matter doesn't fall directly onto the neutron star's surface. Because the matter has angular momentum from the orbital motion of the binary system, it spirals inward, forming a rapidly rotating disk of gas around the neutron star called an accretion disk. The accretion disk is hot, bright, and dynamic. Temperatures in the inner regions of the disk can reach millions of degrees as gravitational energy is converted to heat through friction. Matter spirals inward through the disk, losing energy through friction and radiation, gradually working its way closer to the neutron star. The disk glows brightly in X-rays, visible to orbiting X-ray telescopes across enormous distances. When matter finally reaches the neutron star's surface, it slams into the crust at nearly the speed of light, releasing an enormous amount of energy as X-rays. The impact of infalling material on a neutron star's surface releases more energy per kilogram than nuclear fusion. Systems like this are observed as X-ray binaries, binary star systems that are among the brightest X-ray sources in the sky. But here's the crucial part. The matter falling onto the neutron star carries angular momentum. As it hits the surface, it transfers that angular momentum to the neutron star, spinning it up. It's like pushing a merry-go-round. Each push adds a little more rotational energy. Over millions of years, a continuous stream of matter falling onto the neutron star gradually increases its spin rate. Slowly at first, then faster and faster as more matter accumulates and more angular momentum is transferred. The neutron star might accrete as much as 1/10 of a solar mass or more during this process, enough to noticeably increase its total mass. And all of that accreted material, arriving with angular momentum from the disk, accelerates the neutron star from a slow spin of perhaps once every few seconds back up to hundreds of rotations per second. The entire process is like winding a clock, except the clock is a dead star, and the winding mechanism is an entire companion star being slowly consumed. At the same time, the accretion process also weakens the neutron star's magnetic field. The exact mechanism is still debated, but observations clearly show that millisecond pulsars have magnetic fields roughly 10,000 times weaker than ordinary pulsars. Instead of a trillion Gauss, a millisecond pulsar might have a magnetic field of only about 100 million Gauss. That's still enormously strong by any terrestrial standard, but it's far weaker than an ordinary neutron star's field. This weakened magnetic field turns out to be crucial for the long-term survival of the millisecond pulsar, something we'll explore in detail shortly. Eventually, the companion star stops transferring matter. Perhaps it has lost most of its outer layers and has shrunk back within its Roche lobe. Perhaps it has been completely consumed, reduced to a tiny white dwarf, or even evaporated entirely by radiation from the accretion process. Whatever the reason, the mass transfer stops. The accretion disk disperses, and what's left is a neutron star spinning hundreds of times per second with a relatively weak magnetic field, sitting in a binary system with whatever remains of its companion. This newly spun up neutron star is now a millisecond pulsar. It has been recycled, taken from a state of slow rotation and silence, and brought back to rapid rotation and active pulsing through the transfer of matter and angular momentum from a companion star. The process takes millions of years, but the result is a pulsar that can remain active for billions of years more, far longer than the ordinary pulsars that were born spinning fast and have been slowing down ever since. Astronomers have actually caught this recycling process in action. There are several known transitional millisecond pulsars, systems that have been observed switching back and forth between an accretion-powered X-ray binary state and a rotation-powered millisecond pulsar state. In one mode, the system is an X-ray binary, with matter streaming from the companion onto the neutron star, producing bright X-ray emission. In the other mode, the mass transfer has temporarily stopped, and the neutron star is visible as a radio millisecond pulsar, pulsing away at hundreds of rotations per second. These transitional systems provide direct evidence that millisecond pulsars are indeed recycled from old neutron stars through accretion. The timing precision of millisecond pulsars is even more impressive than that of ordinary pulsars. Because they spin so much faster, each rotation takes only a few milliseconds, which means there are many more pulses to average over in any given observation period. And because their magnetic fields are weaker, the torques slowing them down are much smaller, making their spin rates even more stable. Some millisecond pulsars have timing stabilities comparable to the best atomic clocks in the world. They lose or gain less than a microsecond over a decade. Their periods can be predicted years in advance with nanosecond accuracy. This extraordinary precision has enabled one of the most ambitious experiments in modern astronomy, the Pulsar timing array. The concept is elegant and profound. By monitoring an array of millisecond pulsars spread across the sky, astronomers can detect gravitational waves passing through our region of the galaxy. The idea is that a gravitational wave, a ripple in the fabric of space-time, would cause tiny changes in the distances between Earth and the pulsars in the array. These distance changes would show up as tiny variations in the arrival times of the pulsars. By looking for correlated timing variations across many pulsars, astronomers can distinguish the effect of a gravitational wave from random noise. This is different from the gravitational waves detected by the LIGO and Virgo observatories, which detect high-frequency gravitational waves produced by colliding neutron stars and black holes. Pulsar timing arrays are sensitive to much lower frequency gravitational waves with periods of years to decades. These low-frequency waves are thought to be produced by supermassive black hole binaries, pairs of enormous black holes orbiting each other at the centers of merging galaxies. In 2023, multiple pulsar timing array collaborations around the world, including the North American Nanohertz Observatory for Gravitational Waves, the European Pulsar Timing Array, the Parkes Pulsar Timing Array, and the International Pulsar Timing Array, announced strong evidence for a gravitational wave background. a constant hum of low-frequency gravitational waves permeating all of space. This background is thought to be the combined signal of many supermassive black hole binaries throughout the universe, all producing gravitational waves that overlap to create a persistent, low-level rumble in the fabric of space-time. This detection was possible only because millisecond pulsars keep such precise time. The gravitational wave signal they detected corresponds to timing variations of perhaps a few tens of nanoseconds, tens of billionths of a second, measured across distances of thousands of light years. The fact that we can detect such incredibly tiny timing variations in signals from dead stars thousands of light years away is a testament to both the precision of millisecond pulsars and the ingenuity of the astronomers who study them. Pulsars have also been used to test general relativity in ways that go beyond the Hulse-Taylor binary. In 2003, astronomers discovered a system called the double pulsar, PSRJ 0737-3039, in which both neutron stars are visible as pulsars. This is the only known system where both objects in a binary are observable pulsars. The system has allowed extraordinarily precise tests of general relativity. The two pulsars orbit each other every 2 hours and 27 minutes, moving at speeds up to 1 million kilometers per hour. The gravitational effects are extreme. The orbital precession, the slow rotation of the orbit's orientation in space, is enormous compared to anything in the solar system. Mercury's orbital precession, which was one of the original confirmations of general relativity, amounts to 43 arcseconds per century. The double pulsar's orbital precession is about 16.9 degrees per year. That's roughly 140,000 times faster than Mercury's. General relativity predicts this precession rate precisely, and the observed rate matches the prediction to within a tiny fraction of a percent. The double pulsar also allows measurement of other relativistic effects. Gravitational redshift, time dilation, the Shapiro delay, where signals from one pulsar are delayed when they pass close to the other pulsar, because the signal has to travel through curved space-time near the companion. All of these effects have been measured and all agree with general relativity's predictions to extraordinary precision. The double pulsar system is currently the best laboratory in the universe for testing general relativity in the strong field regime, conditions where gravity is so intense that the differences between general relativity and alternative theories of gravity become measurable. Every prediction Einstein's theory makes about this system has been confirmed. Every test it has been subjected to, it has passed. A century after general relativity was first proposed, pulsars continue to provide its most stringent confirmations. Beyond these headline discoveries, pulsars serve as cosmic tools in many other ways. The signals from pulsars pass through the interstellar medium, the thin gas that fills the space between stars. As the pulsar signal travels through this gas, it's affected in measurable ways. Lower frequency radio waves travel slightly slower through the interstellar medium than higher frequency waves, an effect called dispersion. By measuring how much the signal is dispersed, astronomers can estimate how much interstellar material lies between Earth and the pulsar. This provides a way to map the distribution of gas in the galaxy. Pulsars have also been used to study the magnetic field of the Milky Way itself. As the polarized radio signal from a pulsar passes through magnetized interstellar gas, its plane of polarization rotates, an effect called Faraday rotation. The amount of rotation depends on the strength of the magnetic field and the density of the gas along the line of sight. By measuring this rotation for many pulsars distributed across the sky at known distances, astronomers can build up a three-dimensional map of the galactic magnetic field. This would be nearly impossible without pulsars, since the galactic magnetic field is far too weak to detect directly from Earth. Pulsars essentially act as backlit probes, their signals carrying an imprint of everything they pass through on their way to our telescopes. Some pulsars have been proposed as the basis for a galactic navigation system. Because millisecond pulsars have such stable and predictable timing signatures, and because each pulsar has a unique combination of period, position, and pulse profile, a spacecraft equipped with an X-ray telescope could potentially determine its position in the galaxy by measuring the arrival times of pulsars from several known pulsars and triangulating. NASA has actually tested this concept with an experiment called Sextant on the International Space Station, using the NICER X-ray telescope to demonstrate autonomous navigation using millisecond pulsars. The experiment showed that a spacecraft could determine its position to within about 5 kilometers using pulsar signals alone, with no input from Earth-based tracking stations. 5 kilometers of accuracy, determined entirely by timing signals from dead stars scattered across the galaxy. No GPS satellites needed, no ground control, just the predictable, unwavering pulses of spinning neutron stars, serving as celestial beacons. This idea of using pulsars for navigation highlights something profound about these objects. They're so reliable, so predictable, so stable, that they can serve as the fixed reference points for navigation across an entire galaxy. In a universe where everything moves and changes, where stars are born and die, where galaxies collide and merge, where civilizations might rise and fall across thousands of light years, pulsars stand as some of the most stable structures that exist. Their timing is among the most predictable phenomena in all of nature. They are, in a very real sense, the heartbeats of the cosmos. Steady, rhythmic, and enduring far beyond anything else the universe has produced. But that stability is not absolute. Pulsars do change. They slow down, they lose energy. And over very long timescales, they eventually stop pulsing altogether. The question is how long this takes. How long can a pulsar keep going before it fades into silence? And the answer, particularly for millisecond pulsars, turns out to be almost incomprehensibly long. Long enough to challenge our notion of what it means for something to stop. Because a millisecond pulsar doesn't die quickly. It barely dies at all on any time scale that has meaning for human civilization, or even for the age of the universe itself. And understanding why requires us to look at what happens to a pulsar's rotational energy over time, how it radiates that energy away, and what determines the moment when the spinning finally, inevitably, comes to an end. But nothing in the universe lasts forever unchanged. Not stars, not galaxies, not even the spin of a dead stellar remnant in the vacuum of space. So here is the honest question. If a pulsar is losing energy with every rotation, why does it seem to never stop? And the truth is more nuanced than those words suggest. A pulsar does stop, eventually. But the word eventually is doing an enormous amount of work in that sentence. For some pulsars, eventually means millions of years. For others, it means billions. And for the most stable millisecond pulsars, eventually means timescales so long that the universe itself will have changed beyond recognition before the spinning finally ends. Let's start with the basic physics. A pulsar's rotation is not being maintained by any engine or energy source. The neutron star is not burning fuel to keep spinning, it's coasting. It was set spinning by the conservation of angular momentum during the supernova collapse, and since then, it has simply been spinning in the vacuum of space. There's nothing adding energy to the rotation. The spin is a reservoir of energy that was filled at birth and has been draining ever since. The drain is slow, but it's real, and the mechanism is the magnetic field itself. The same magnetic field that creates the beams of radiation, the same field that makes the pulsar visible to us across thousands of light years, is also the thing that's killing it. Slowly, steadily, inevitably. Every rotation, the tilted magnetic field radiates energy. This is called magnetic dipole radiation. A rotating magnetic dipole, which is what a pulsar essentially is, emits electromagnetic radiation at the rotation frequency. This radiation carries energy away from the system, propagating outward at the speed of light into surrounding space, never to return. And that energy comes from the rotational kinetic energy of the neutron star. As energy is radiated away, the rotation slows. The star cannot replace what it loses. It can only spend what it has. In addition to magnetic dipole radiation, the pulsar also loses energy through the particle wind it drives. The pair cascade above the magnetic poles doesn't just produce the beams of radiation we detect as pulsars. It also produces a continuous outflow of relativistic particles, electrons and positrons streaming away from the neutron star at nearly the speed of light. This pulsar wind carries energy and angular momentum away from the star, further contributing to the slowdown. In some pulsars, particularly young and energetic ones, the pulsar wind carries away more energy than the dipole radiation itself. The wind slams into the surrounding medium, the interstellar gas or the remnants of the supernova explosion, and creates a shockwave where the particles are further accelerated and produce intense radiation. The Crab Nebula provides the most beautiful and well-studied example of this. The Crab pulsar, at the center of the nebula, is injecting energy into the surrounding gas through its pulsar wind. The nebula itself glows because of this energy input. The synchrotron radiation from particles accelerated by the pulsar wind illuminates the entire nebula across the electromagnetic spectrum, from radio waves to X-rays. Deep inside the nebula, surrounding the pulsar, you can see the wind termination shock, the boundary where the relativistic wind from the pulsar collides with the slower moving nebular material. Wisps and jets of glowing gas trace the flow of energy from the tiny pulsar outward into the expanding cloud. The energy powering all of this glow, every photon emitted by the Crab Nebula across every wavelength, comes directly from the Crab pulsar's rotation. Every photon represents a tiny amount of rotational energy stolen from the spinning neutron star at its center. The nebula is literally being powered by the spin of a dead star. The Crab pulsar is slowing down at a measurable rate. Its period is currently about 33 milliseconds, meaning it spins roughly 30 times per second. But that period is increasing by about 38 nanoseconds per day. That sounds tiny, and it is tiny on human timescales. You wouldn't notice the difference from one day to the next, but over years and decades, it adds up. The Crab pulsar is spinning measurably slower now than it was when it was first discovered in 1968, and it's spinning much slower now than it was when it was born in the supernova explosion of 1054. At that time, it was probably spinning at close to 100 rotations per second. In roughly 1,000 years, it has slowed from 100 to 30. That's a significant loss of rotational energy. The rate at which a pulsar slows down depends primarily on two things: the strength of its magnetic field and its current rotation rate. Stronger magnetic fields produce more magnetic dipole radiation and drive more intense particle winds, draining the rotational energy faster. Faster rotation also means more energy is radiated per unit time. So pulsars with strong magnetic fields and fast rotation rates slow down the fastest, while pulsars with weak magnetic fields and slower rotation rates slow down the most gradually. This is where the distinction between ordinary pulsars and millisecond pulsars becomes crucial for understanding longevity. Ordinary pulsars have strong magnetic fields, roughly 1 trillion Gauss. These strong fields cause relatively rapid spin down. A typical ordinary pulsar might have a characteristic age of a few million to a few tens of millions of years. The characteristic age is an estimate of how long the pulsar has been spinning, calculated from its current period and its rate of slowdown. It's not always an accurate measure of the true age, but it gives a rough sense of the timescale involved. Within a few million years, an ordinary pulsar slows down considerably. Within a few tens of millions of years, many ordinary pulsars have slowed to the point where they can no longer produce detectable radio emission. This brings us to one of the most important concepts in pulsar physics: the death line. Astronomers plot pulsars on a diagram with a rotation period on one axis and the rate of period change on the other, or equivalently, the period on one axis and the magnetic field strength on the other. This is called the PP dot diagram, and it's one of the most important tools in pulsar astronomy. When you plot all known pulsars on this diagram, a clear pattern emerges. Pulsars cluster in certain regions and are absent from others. Young, energetic pulsars sit in the upper left, with short periods and high spin-down rates. Older pulsars migrate toward the lower right as they slow down and their energy output decreases. Millisecond pulsars occupy their own distinct island in the lower left, with short periods but very low spin-down rates, reflecting their weak magnetic fields. And there's a region in the lower right of the diagram corresponding to long periods and weak magnetic fields, where no pulsars are found. The boundary of this empty region is the death line. The death line represents a physical limit. For a pulsar to produce radio emission, it needs to generate the pair cascade above its magnetic poles. The pair cascade requires strong enough electric fields to accelerate particles to the energies needed for gamma-ray photon production and subsequent pair creation. These electric fields are generated by the rotating magnetic field. As the pulsar slows down and its magnetic field weakens with age, the electric fields near the poles decrease. Eventually, the voltage drop across the polar cap falls below the threshold required to initiate the pair cascade. At that point, the electric fields become too weak to sustain it. Without the pair cascade, there are no relativistic particles streaming along the magnetic poles. Without those particles, there is no beam of radiation. The pulsar goes dark. It crosses the death line and enters the graveyard region of the PP dot diagram. When a pulsar crosses the death line, it doesn't explode. It doesn't collapse. It doesn't change in any dramatic physical way. The neutron star is still there, still spinning, still possessing a magnetic field, but it can no longer produce the conditions necessary for radio emission. It becomes a silent neutron star, spinning quietly in the dark, invisible to radio telescopes. It has crossed the threshold below which the pulsar mechanism can no longer operate. The lighthouse has gone dark, not because the lighthouse was destroyed, but because the bulb has dimmed below visibility. How long does it take for an ordinary pulsar to reach the death line? It varies depending on the initial conditions, but for a typical ordinary pulsar with a magnetic field of around 1 trillion Gauss and an initial spin period of a few tens of milliseconds, the timescale is roughly 10 million to 100 million years. That sounds long by human standards, and it is. But by cosmic standards, it's brief. The universe is 13.8 billion years old. The Milky Way has been forming stars for over 10 billion years. A pulsar that lasts 100 million years is active for less than 1% of the galaxy's history. Most ordinary pulsars that were ever created in the Milky Way have long since crossed the death line and gone silent. The pulsars we observe today are the relatively recent ones, born in supernovae within the last few million to few tens of millions of years. The overwhelming majority of neutron stars in the galaxy are not active pulsars. They're dead pulsars, silent spinners that crossed the death line long ago and now drift invisibly through the galaxy. Estimates suggest there are roughly 1 billion neutron stars in the Milky Way. Of those, perhaps 100,000 to 200,000 are currently active as observable pulsars. That means the vast majority, more than 99.9% of all neutron stars, are silent. They've either crossed the death line, or their beams don't point toward Earth, or both. The galaxy is filled with the ghosts of dead pulsars, neutron stars that once swept their beams through space like lighthouses, but have long since gone dark. They drift invisibly through the galaxy, impossible to detect without extremely sensitive instruments. Occasionally one might be spotted through its thermal X-ray emission or through its gravitational effects on a companion star. But for the most part, these dead pulsars are invisible, wandering the galaxy like silent tombstones, marking where stars once died. But now let's turn to millisecond pulsars, because their story is completely different. We've already seen that the recycling process leaves millisecond pulsars with drastically weakened magnetic fields. And it's this weakness, paradoxically, that gives them their extraordinary longevity, because the rate at which a pulsar slows down depends directly on the strength of its magnetic field. A field 10,000 times weaker means a spin-down rate that's roughly 1 million times slower. A weaker field means less magnetic dipole radiation, a weaker particle wind, and therefore a much slower drain on the rotational energy. The slowdown rate of a millisecond pulsar is typically 1 million times lower than that of an ordinary pulsar. Let me put that in concrete terms. The Crab pulsar, an ordinary young pulsar with a strong magnetic field, is slowing down at a rate of about 38 nanoseconds per day. That means its period increases by about 14 microseconds per year. Over 1 million years, its period would increase by about 14 seconds, which is an enormous change. The Crab pulsar is losing a rotational energy rapidly, and its active lifetime is limited. Now compare that to a typical millisecond pulsar. A well-studied millisecond pulsar might have a period change rate so small it's almost unmeasurable, roughly a few picoseconds per year. Not microseconds, not even nanoseconds, picoseconds, trillionths of a second per year. At that rate, the pulsar's period would increase by 1 second over the course of roughly 17 trillion years. That is more than 1,000 times the current age of the universe. After 10 billion years of continuous slowdown, a millisecond pulsar's period would have changed by less than 100 nanoseconds. It would still be spinning hundreds of times per second, still far above the death line, still actively pulsing. The characteristic ages of millisecond pulsars, calculated from their periods and slowdown rates, are typically billions of years. Some have characteristic ages comparable to the age of the universe itself. These objects have been spinning since long before Earth existed. They were already ancient when the solar system formed 4.5 billion years ago. Some millisecond pulsars have been spinning for longer than most stars in the galaxy have been alive. They're among the most enduring active phenomena in the known universe. How long can a millisecond pulsar remain active? Theoretical estimates suggest that the most stable millisecond pulsars, those with the weakest magnetic fields and the fastest rotation rates, could remain above the death line for 10 billion years or more. Some might persist for tens of billions of years, far longer than the current age of the universe. The universe is only 13.8 billion years old, and some millisecond pulsars have predicted active lifetimes that exceed this. They could, in principle, outlive the current age of the cosmos several times over before they finally slow enough to cross the death line. In principle, there are millisecond pulsars active today that will still be pulsing long after the sun has exhausted its fuel, swelled into a red giant, and collapsed into a white dwarf. They will still be pulsing after most of the stars currently visible in the night sky have died. They will still be sweeping their beams through the darkness of a galaxy that has grown older and quieter. A galaxy where star formation has slowed and the bright young stars have faded, but where these ancient recycled pulsars continue their patient rotations, ticking away like cosmic metronomes that have outlasted nearly everything around them. This is what the title means when it says a pulsar never stops. It doesn't mean literally never. Given infinite time, every pulsar will eventually slow down enough to cross the death line. The energy reservoir is finite. The drain is real. Entropy always wins in the end. But the timescales involved, especially for millisecond pulsars, are so vast that from any practical standpoint, from the standpoint of human civilization, from the standpoint of the galaxy's current lifetime, from even the standpoint of the age of the universe, these objects are effectively permanent. They don't stop on any timescale that has meaning for us or for anything we can observe. They simply persist, spinning and pulsing and sweeping their beams through a universe that changes around them while they remain essentially the same. There's something both beautiful and eerie about this. A millisecond pulsar is a dead star. The massive star it came from is gone, destroyed in a supernova millions or billions of years ago. The companion star that spun it back up may be gone too, consumed or reduced to a tiny remnant. Everything about the original system has changed beyond recognition. But the neutron star persists, spinning at hundreds of rotations per second, pulsing with clockwork precision, a relic from a time when the galaxy was different, when different stars shone and different planets orbited them. It carries in its spin a memory of angular momentum that was imparted billions of years ago. Every rotation is an echo of events that happened before Earth existed. There are occasional disruptions to this steady spinning. Pulsars sometimes experience sudden, small increases in their rotation rate called glitches. A glitch is a sudden speed up, an abrupt decrease in the pulse period, followed by a gradual recovery back toward the pre-glitch slowdown rate. Glitches are thought to be caused by the interaction between the neutron star's solid crust and the superfluid interior. The superfluid, which rotates through quantized vortices, can store angular momentum separately from the crust. As the crust slows down due to magnetic braking, the superfluid continues spinning at its original rate. A differential builds up between the rotation rate of the crust and the rotation rate of the superfluid. Eventually, this differential becomes large enough that vortices in the superfluid suddenly unpin and transfer angular momentum to the crust, causing it to speed up abruptly. The crust lurches forward. The pulse period suddenly decreases. Then the slow process of magnetic braking resumes, and the crust begins to slow down again, gradually restoring the differential until the next glitch occurs. Glitches are common in young pulsars. The Vela pulsar, a relatively young pulsar about 11,000 years old, spinning roughly 11 times per second, glitches roughly every 3 years. Each glitch changes its rotation rate by a tiny amount, typically a few parts in a million. The crab pulsar also glitches regularly. Millisecond pulsars, by contrast, rarely if ever glitch. Their crusts and superfluids seem to be more tightly coupled, preventing the buildup of large differentials. This is another reason millisecond pulsars are such superb timekeepers. They don't suffer the sudden timing irregularities that affect younger pulsars. There's another type of timing irregularity called timing noise, a slow, random wandering of the pulse arrival times that can't be predicted. Timing noise is most prominent in young pulsars and is thought to be related to instabilities in the magnetosphere or to interactions between the superfluid interior and the crust. Millisecond pulsars have much less timing noise than young pulsars, again making them superior for precision timing applications. So when you put it all together, the full picture of a pulsar's life looks something like this. A massive star dies in a supernova, leaving behind a rapidly spinning neutron star with a powerful magnetic field. This young pulsar begins life spinning many times per second, sweeping its beams through space and gradually slowing down as it radiates energy through its magnetic field. Over millions of years, it slows considerably. Over tens of millions of years, it may cross the death line and go silent, becoming just another invisible neutron star drifting through the galaxy. Most neutron stars in the Milky Way have reached this fate. But if the neutron star happens to be in a binary system with a companion star, it gets a second chance. When the companion evolves and begins transferring matter, the neutron star is spun back up to hundreds of rotations per second. Its magnetic field is weakened in the process. And when the mass transfer ends, the recycled neutron star emerges as a millisecond pulsar with a weak magnetic field and an extraordinarily slow spin-down rate. This millisecond pulsar can remain active for billions of years, far longer than the ordinary pulsar it once was. It becomes one of the most enduring objects in the universe, a dead star that outlasts living ones, a remnant that persists long after the systems that created it have vanished. And this brings us to the deepest implication of the pulsar story. What does it mean for an object to persist this long? What does it mean for something to keep doing the same thing? Rotation after rotation, pulse after pulse, for billions of years. Consider the timescales involved. A millisecond pulsar with a characteristic age of 10 billion years has been spinning since before the Earth formed. It was already ancient when the first single-celled organisms appeared in Earth's oceans. It was pulsing steadily when the first fish evolved, when the first plants colonized the land, when dinosaurs ruled the earth, when mammals emerged, when the first humans looked up at the night sky and wondered what the stars were. It was pulsing through all of human history, through the invention of agriculture, through the rise and fall of every empire, through every war and every peace, through the Industrial Revolution, through the space age, and it continues now in this moment as if it has always been here and always will be. And it will still be pulsing long after everything we know has changed beyond recognition. If you could somehow listen to a millisecond pulsar, converting its radio pulses into sound, you would hear a steady tone, a hum at a frequency of several hundred cycles per second. That hum has been sounding for longer than our planet has existed. It will continue sounding for longer than our sun will shine. It is one of the most constant, most unchanging things in a universe that is otherwise characterized by change, by birth and death, by creation and destruction. Stars ignite and burn out, galaxies collide and merge, civilizations might rise and fall on planets we will never see. But through all of this, somewhere in the galaxy, a neutron star no wider than a city continues its patient rotation, sweeping its beams through the void with the same rhythm it has maintained for eons. There's a question that sometimes comes up when people learn about pulsars. If they're so precise, if they keep such perfect time, are they really natural? Could they be artificial beacons placed by an advanced civilization to serve as navigational markers across the galaxy? This was the question that occurred to Jocelyn Bell Burnell and Anthony Hewish when they first detected pulsars in 1967. The regularity seemed too perfect to be natural. The signal was so clean, so periodic, so unlike anything else in the sky, that an artificial origin seemed at least worth considering. But we now know they're natural. We understand the physics completely. The rotation of a neutron star, the misalignment of its magnetic field, the pair cascade, the lighthouse effect. All of it follows from well-understood laws of physics. No intelligence is required. No engineering, no design, just the inevitable consequences of a massive star dying and leaving behind a rapidly spinning, strongly magnetized remnant. We can predict how fast they should spin, how quickly they should slow down, what their magnetic field should be, and what radiation they should produce. And the predictions match the observations. The universe produces these objects naturally, through processes that are violent and chaotic, and yet the result is something of extraordinary precision and endurance. Order emerging from chaos, regularity arising from catastrophe, a clock born from an explosion. Perhaps that's the most remarkable thing about pulsars. Not their density, not their magnetic fields, not their rotation speeds, but the fact that such precision, such reliability, such endurance can arise from such violence. A supernova is one of the most destructive events in the universe. It destroys the star. It scatters its outer layers across light years. It can sterilize nearby planetary systems with irradiation. And yet, at the center of all that destruction, it creates something that will outlast almost everything else the universe produces. A tiny, dense, magnetized sphere spinning with clockwork precision for billions of years. A lighthouse in the void that never truly goes dark. When you look up at the night sky tonight, you won't see any pulsars. They're far too faint and their pulses far too rapid for human eyes to detect. But they're there. Scattered across the Milky Way, thousands of them are pulsing right now. Some are young, spinning dozens of times per second, surrounded by the expanding remnants of the supernova explosions that created them. Some are ancient millisecond pulsars, spinning hundreds of times per second, their progenitor stars long forgotten, their companion stars consumed or reduced to faint remnants. Each one is sweeping its beams through the darkness with mechanical precision. Each one is a clock that has been ticking for millions or billions of years. Each one is a dead star that refuses to go completely silent. Somewhere out there, right now, a neutron star 12 miles wide is completing 700 rotations every second. It has been doing this for longer than the Earth has existed. The star that created it is gone. The companion that spun it up is a small, faint star, bloated and irradiated, locked in a tight orbit with the neutron star it helped resurrect. The galaxy around it has changed profoundly since this pulsar was born. Stars have formed and died. Planetary systems have come and gone. Perhaps civilizations have risen and fallen on worlds we will never know about. And through all of that, this tiny dead star has been spinning, pulsing, sweeping its beams through the cosmos with a regularity that would put the finest Swiss clockmaker to shame. It will still be spinning when our sun burns out. It will still be pulsing when the last stars in the Milky Way begin to flicker and fade. It carries in its rotation a memory of angular momentum from a time before our world existed, and it will carry that memory forward into a future we cannot imagine. A dead star, no wider than a city, announcing its presence to the entire universe with every single turn, never truly stopping, never truly going silent, just gradually, imperceptibly, impossibly slowly, winding down across timescales that dwarf everything human beings have ever known or will ever know. That is what a pulsar really is. And that is why, for all practical purposes, for all timescales that matter to anyone who will ever live, it never stops.